Testing 1 2 3. Right. We continue from last time where we stopped at section 10.2. Right. So what did we learn last time? I mean the very last thing that we put together, right? Which is the geometric sequence. And the key here is it's a sequence. So meaning that an individual term on a list. So we're talking about one particular term. And so if we let R be a real number, then R to the n will be a geometric sequence. For example, it will be like this. If R go, I put examples. For example, let's say we talk about this sequence. One half to the n power when n equal to 1 to infinity. Let's say 0 to infinity. So in that case, this sequence 1 half to the 0 power. So I have 1 half, 1/4, and so on. So that is called a geometric sequence. We have something to an n power, and that will go to 0 if R absolute value of R is less than 1, meaning that is between -1 and 1, and equal to 1 if R is 1 and does not exist if absolute values of R greater than 1. So pretty much outside of -1 and 1 that does not exist. Between -1 and 1 equal to 0 and equal to 1. That's what we have. And when if R is positive, all of them will be positive, and it is monotonically either convergent or divergent, decreasing or increasing correspondingly. And if R less than 0, the sign will change from positive to negative. Right. So that's what we have from last time. We have this example. So R go 3/2, R go to -1/3, and then so on. Of course, that's what we have from last time. Now we continue. Still a little off. Right. Next we have what we call the Sweet theorem. What section is this? 4 C Square theorem. So if we have three sequence, if we have three sequence and in this order, B sub n is between A sub n and C sub n. Greater than some index n, and if both the left and the right term go to 0, the middle one go to 0 as well. And the limit. Right. So this just like the Square theorem for function, but this time we have for a sequence D. Find the limit of the sequence. I should have that sequence. Right. So, just like in the Square theorem, we have to make sure that we have to find the boundary, something greater than and something less than, but most importantly, both of the boundary have to come to the common limit. So, and the easiest example usually with the Square theorem is where we have cosine or sine of something between -1 and 1. So, right? So sine and cosine will be between -1 and 1. So it could be cosine, it could be sine, it doesn't matter. We start with cosine of n is less than equal to 1 and greater than equal to -1. And then we can divide by n squared plus 1 on both sides. Now, just need one thing. Be mindful when we divide by a number in inequality. So we divide by a positive number. We don't switch inequality, so that will stay the same. And now the rest is simple. As n goes to infinity, n goes to infinity, we have a finite number divided by infinity. So this one goes to 0. And this one goes to 0 as well when n goes to infinity. And of course, if both ends go to 0, the middle has to go to 0. So we have limit of cosine of n over n squared plus 1 as n goes to infinity equal to 0. Yeah, sorry about that. I had some frames rot again, so that should be a lag, but it should be okay now, right? Right, I think it's fine now. And then we go to just write this theorem. We'll get back to this later. It could be due to a computer, my computer, or due to the internet. I don't know, but I look at the stream statistic and then I can tell, but I still don't know from what end. Right. So it said bounded, meaning there's an upper bound and there's a lower bound or lower bound, and monotonic is either increasing or decreasing. Right. Actually, let me be a little more precise. When we say bounded, could be bounded above or below. Now it's dropped again. Why those go to 0? Because 1 or negative 1, those are constant. All we have finite, negative 1 or 1 are finite, and n squared plus 1 is infinity. A finite divided by infinity is 0. So that's why both of these go to 0, because we have a constant or finite number on the top. Why should write like this instead? Put like negative 1. So negative 1 is still finite, divided by n squared plus 1. So that's what we have. Right. So when we write bounded, we mean bounded above by below, and monotonic is either non-increasing or non-decreasing. I just going to draw one example real quick. Let's say there is a bound, a monotonic sequence. So it is either, in this case, is non-decreasing, and there's a bound, so there will be a limit, or we have a function on the top, and that is non-increasing. Either way, if there is a bound, then there will be a limit. Right. The next part is very important, as I mentioned before. Progress. Right. So we don't have to write that. We mean the symbol, the two less than sign. So we know the symbol means. So we just say let P, Q, R, and S be positive, and the base B be greater than 1. Right. So we have the sequence, and this time we write that in terms of sequence instead of particular terms. So ln of q to the n, that is q. N to any power, n to any power times ln of any power, p plus s b to the n, sorry, n factorial and n to the n. So that is the theorem. By the way, what we're going to put on the card, what do you need to write on the test? I mean, you need this for the test. Oh, before we write that, we just write this little note. This ranking do not change if it is multiplying if a sequence is multiplying by a positive constant. Right. Now, this will come in handy when we take the test, even though it looks like all the bells and whistles are there, but the simplifying version of this, that's what we really need is we start with a constant. Of course, the constant does not go to infinity, right? So we start with, I'm not sure this is enough though, but we'll try. So we start with a constant. And then we have ln. I'm want to write as a function of n. So ln of n, and then n to the p power. Right, and then we skip all of that. B to the n, n factorial, and n to the n. Right. Have this one in handy. We'll refer back to this more often than not. The constant, of course, the constant -1 and 1 is going to be bigger than cosine and sine will be between -1 and 1. So a few things here. When we write this power, this will be expanded to for example, we might have n to the 1/2. Of course, it's going to be less than n. Going to be less than going to be n squared. Something like that. For example, this we mean is when n goes to infinity, only the one with the highest power matters. So the one with the higher power will be bigger than the one with the smaller power. So that one we're expanding from there. And the constant here, we can expand that. This we'll use a few times, more than a few times. We have sine or cosine. And that is for the constant here. Right, so -1 and 1, those are constant. Between it is sine or cosine, and that is less than ln, and that is less than n to the p power, less than b to the n power, and then less than factorial, and less than n to the n power. And when we write like this, p is positive numbers and b is bigger than 1, so p bigger than 0 and b is bigger than 1. Right, so we'll refer to this a few more times, so that's why I write on the 3x5 card. Get back to this in a minute. Example. Right. Compare the following sequence. As n goes to infinity. Right, so we have those two things. Right, first, let's say ln of n to the 10 power. Let that be h of n. We have the properties of ln that says when we have 10, when there's a power, that power going outside. Right? By the way, it is also important to note that when we write like this and this is different. For example, ln of n squared is different than ln of n squared. This is like when we write sine squared, meaning this term, meaning ln of n squared. Notice the difference. For this one, we can check the power outside. For this one, we cannot. Right. So we have that. Now let's say b of n is 0.01 n. Now we have the important note here. The ranking here do not change if it's multiplied by a constant. So we just ignore a constant and we compare that term and that term only. And according to the ranking that we have here, Ln is less than n raised to any power. Right. So h of n grows slower than b of n. Right, simple enough. 2. How about n factorial and 10 to the n? Right. So we have the n factorial is bigger than any constant to the n power. So this is like b to the n power. And this of course n factorial. And according to this ranking, the n factorial is growing faster. So we say, put that in the sequence term. N factorial right. So like that, keep this in handy. We refer to this many times. Right. And finally, the definition of the limit of a sequence. This is the precise definition. And this is the limit of the sequence. Right. I'm just gonna have to write that. The sequence has the unique limit if given any epsilon positive, there exists a positive number n such that h of n minus L less than epsilon whenever n greater than big N. Right, so that's just like the definition of limit, but this time we write the definition of the sequence. So we write using that, and of course when we set the limit of a sequence, we mean the limit of a sequence when n goes to infinity. Right. If the limit exists we say the sequence converges to L. Otherwise, it is said to be divergent. Right, so that's just a precise definition of the limit of a sequence. By the way, before we go to the next section, it is very important that to distinguish between what we learn in this section and the next one. In this section, what we learn about is a sequence, meaning a term in a list. Or I mean, a sequence is a list, but we focus on an individual terms and not as a whole. So again, sequence refer to just a term in a sequence, not the whole thing. And when we say the limit of a sequence, we mean that the limit of the sequence when n goes to infinity, and not any particular number. Right, with that we go to section 10.3. Yeah, I have some frame drop again, but didn't know when was that, but right, so 10.3. Infinite sequence. I'm sorry, infinite series. The difference between a series and a sequence is that a series is the sum of the sequence. To distinguish to what to other things, when we write infinite series, we mean the sum of every term in the sequence. So series is a sum. A sequence is one term. I mean, of course, the sequence is the list of a bunch of terms, but we talk about individual one. The series is the sum of everything, the whole series, the whole sequence. Right, so we have those properties. Right, suppose if we add all the term in the sequence AK, or we have the series, this is a series, AK by itself is a term of a sequence. Right, so we have that equal to A, and C is any number. Then we can just take the constant outside. And also note that I write like this to save space. I write this to save space, but by default it is always infinite series, so it go from 0 or 1, it doesn't matter, but it will go to infinity because of the infinite series. So by default, when we don't write anything, we mean it from 0 to infinity, so we don't need to write that every single time. We take a lot more space, and it should be 2. If the sum is divergence, meaning that it does not equal to anything, then multiply a constant to it, also diverges. 3. If the series AK equal to A and BK equal to B, then the sum of a series is equal to so we can split. So the series of a sum is the sum of the series. Put minus, still the same. Now, if AK and BK diverges, then the sum also diverges. Number 5. Yeah, this is what I'm talking about. When we're talking about the series, whether we go from 1 to infinity or 0, it doesn't matter. So what matter is it go to infinity, whether we go from 1 or from the first term or m, it doesn't matter. So I just write this. This both converge or diverge. Which means it doesn't matter where the series starts. Convergence only depends as long as it go to infinity. That's what the conversion is based on. Right. It does not matter where it starts. Could start 1 or could start m, doesn't matter as long as we end up with infinity. Right. By the way, we just usually when we write the properties of limit, integral, derivative, now sequence, series, all of that have the same kind of thing, but we have to write every single time. Right, now this is more important. This is called the geometric series. Right. Let R be a real number. And if absolute values of R less than 1, then this will start from 0 to infinity. By the way, you should see this formula before. This is in course algebra or pre-calc, is the sum of infinite geometric series. By the way, in this case, A is a constant. Usually referred to as a first term, and R is the common ratio. And when we say R, absolute values of R less than 1, we mean it is between -1 and 1. But if we don't have that, if absolute value of R greater than or equal to 1, the series diverges. Right. So it's very important that we have to check this condition. Just one tiny thing, just want to note that this one of course go to infinity, but this is a not as important note, more like a side note. So if we go instead of to infinity, we go to n, which is a plus ar plus ar squared to the n term. Or we just factor out what a and that will be equal to a r to the n plus 1 minus 1 over r minus 1. 9 terms in the sequence, that is the sum, but in this case we only worry about the infinite series, so that formula. Remember, this is a series, meaning a sum of every terms in the sequence. Right, let's look at some examples. Example 1. Find the sum for the following series. Right. We only need this much space. K equal to 0 to infinity. 2 times 1/3 to the k power. Worry about this? No, I'm just going to put that in here. This is just a review for pre-calculus or course algebra. We don't even need to use that here because most of the problem we do with is infinite series. So we're not worried about the finite case here. Not worry about this. Right. Worry about this. Worry about the theorem itself. Right. So first, now it is very important, and in this theorem, k equal to 0 to infinity, and that r to the power of k. So from here, we have k to 0 power. So that one's good. I kind of put a check mark here. So that one's good. To infinity, so that's good. The power of k, that's also good. So when we write like that, a is going to be 2, right? The constant. And then the term that raised to the k power is r. And then we just need to do this check real quick. Is r, absolute values of r less than 1? And in this case, yes, 1/3 is less than 1 and greater than -1. So absolute values of 1/3 less than 1. So that one check. If this is check, then the sum of the infinite series is equal to a over 1 minus r, which is 2 over 1 minus 1/3. 2 1 minus 1/3 is 2/3. Multiply reciprocal. Cancel out the 2, that gives us 3. So it's simple enough, right? Just make sure that the index will start from 0 to infinity and the power here have to be k. Make sure that it is in that form. Go from 0 to infinity and the index has to be k, because not always we have that. Not always we have everything aligned perfectly like this, like in the next example. Right, so do a little check here. We go from 0 to infinity, which is good in the geometric series, which is good. Now, what is a and what is r? Well, it's not clear when we write like this. So let's rewrite this as I put a -2 on the outside, and then 1 over 5 to the k. Right, and then we have to write the whole thing to the k power like this. So notice that by default 1 raised to the k is also 1, right? 1 raised to any power, still 1. So in which case, we can put both of them inside the power of k, and we have the right form. And then we check, is absolute values of r less than 1, and we have 1/5. So yes, absolute values 1/5 less than 1. So in that case, we can use the formula. A over 1 minus r, negative 2, 1 minus 1/5, sorry, 1 minus 1/5 is 4/5. Oh, I'm not sure what happened today. Yeah. Apparently I cannot do anything, because if I reset or restart the computer, I'm not sure if we can get back to the same video, so we cannot really do that. I'm not sure if I reset my Wi-Fi, I can get back to the same stream. So that's why I cannot do anything. Sorry about that. Right, now this again, check the limits 0 to infinity. It's good. We just need to turn that into the form of that. Need to find a and need to find k. It have to be to the k power. Right, let's see. What do we have? Negative 5 to the k power. So we have the k power, which is good. And then we have k plus 1 power, which is not good. So first, I'm going to split this out. So can I write like that? 3 to the k plus 1 is 3 to the k times 3 to the first. Because when we multiply, we add the power. K plus 1 give us that. No, I still want to keep on the same video. That's why I cannot restart. Anyway, so both of them under the k. So I will put both of them, oh sorry, and then we have 3 at the bottom, and then put 1 on the top. Right? So -5 to the k and 3 to the k. Since both of them under the power of k, we can put them together. Right. Oh, it is in the right form already. So in that case, for this we have a equal to 1/3 and r is -5/3, and we check is absolute value of r less than 1. And we have absolute values of -5/3 is 5/3 is greater than 1. So in that case, that is a no. So it's not a check mark. So that doesn't work. So we said the series diverges. So pretty straightforward. As long we have the limit 0 to infinity, and then pull everything inside, we just have 1 power of k, and the power of k should be on the top, not at the bottom like this. So that's why we have to rewrite in that form. But other than that, if we have a, we have r, the ratio, then we can find the sum easily. Let's take 5-minute break. We continue at 9:05. I mean 9:06. I just reset the connection on my computer. Oh good, we're still on the same stream. I blamed the storm last night. Right. Let's continue. Right, this one is a bit more complicated. Right, this is very complicated because first of all there are two terms and that k is not equal to 0. Right, so I can rewrite this as subtract, so we just split that in two. And then we just do each one of them. Oh, it's not that bad. Let's focus one by one first. But remember, in order to use the formula of a over... In order to use this formula, it has to be going from 0 to infinity. This is not going from 0 to infinity. So how do we make that change? Right, so this is what we can do. First, we can subtract 1 on both sides. So in that case we have k minus 1 equal to 1 minus 1 is 0. Right? And what we do is we're going to let use some different letter like n. So let n equal to k minus 1. In that case it was equal to 0. So more importantly, n equal to k minus 1. If n is equal to k minus 1, so k is equal to n plus 1. Right? If n is equal to k minus 1, then k is equal to n plus 1. Now, in this case, we're going to put, instead of k, we're going to put n equal to 0. Instead of k equal to 1, we can put n equal to 0. Better yet, we should put n plus 1 into here. Don't worry, I'm going to do that for the other one. And then 2 over 3 Since k equal to n plus 1, this is k, we have n plus 1. Right? Now do the same thing for this one. Let n equal to k minus 1. So k is equal to n plus 1. Yeah. The reason we have k minus 1 because if we minus 1 on both sides, that go to 0. Right. Now instead of have k equal to 1, we put n plus 1. Because that is k, right? Of course, I could write like this, but when I write in this form, it was a lot easier to see. 2. K is n plus 1. Substitute that into this k. And that k is n plus 1. Right. Actually, I should write this too. So instead of n equal to 0, instead of k, we set n plus 1 equal to 1. Yeah, that's better. So when we make the substitution, we change the k into n plus 1. Right. Now, subtract 1 on both sides. We have n equal to 0, go to infinity, which is good. 5, 2/3, n plus 1. Same thing, subtract 1 on both sides. N plus 1 minus 1, 2 to the k, 2 to the n. And 7 to the n plus 1. So we make the change in the index, and both of them will go to start from 0. Now, to n plus 1 is to the n, then to the first. Two to the n, and 7 to the n plus 1 is 7 to the n times 7 to the first. Keep doing that. And now if we group this together, 5 times 2/3, 10 over 3. And then we have 2/3 to the n power. And then pull both of them inside the n. We have 1 over 7, 2 over 7 to the n power. And finally, both the ratio between -1 and 1. So we have 10 over 3 over 1 minus 2/3. And subtract 1 over 7, 1 minus 2, 7. So this problem could be a little less complicated, but don't worry. We do that here. So on the homework, make sure that we just change the index. I think I will make one example with the either change in the index. Try this instead. This is probably easier too. Right, let's do that. K equal to 3 to infinity, 81 over 2 to the k power. Right. So first we need this to be 0, right? So we just subtract 3 on both sides. So we have k minus 3 equal to 0. So that is what we let n equal to. So the substitution is let n equal to k minus 3. So add 3 on both sides, k equal to n plus 3. Now we substitute n plus 3 into this k. And then the k is also n plus 3. So that we substitute to the k here. Now n plus 3 equal to 3. If we subtract 3 on both sides, we have n equal to 0 to infinity. And 81 to the 2 to the n times 2 cube. So we have a series that start from 0 to infinity. That is good. That's why we make this change. So it will start from 0. Right. Now 2 to the n. Let's put that at the end. We have 81 over 2 cube. And then 2 to the n by itself, but at the bottom. So we just put 1 on the top so it hold the place. And we can put 1 raised to any power. So both of them will be inside the n. (81 over 8) times 1/2 to the n power. Right. So when we do that, we have a sequence. We have a series in the right form, which is equal to 81 over 8 over 1 minus 1/2. Right. The rest is simple. So this is where we make the change in the index, so that it will be in the right form. Yeah. So on the test, this is probably the most homework, probably the more complicated one, but it will not be as bad as this. Example 2. Write the decimal as fraction. So 0 with 3 repeating. We can write this as 0.3 plus right, which we can factor out 0.3 times 1, 0.1, 0.01, and that 0.1 is 1 over 10, 1 over 100, and so on. And the 1 here we can say 1 over 10 to 0 power. One 10 to the first, and then our bottom line is it should be like this: 110 to 0, 110 to the first, 110 to the second, which is as a summation. And of course that ratio between -1 and 1, so A over 1 minus R one minus that, right. Of course that not much of it's no big deal if we just type long enough number, it will do that as well. So next, we have 1.23 repeating. So the 1 is not repeating, only the 23. So which is 1.23, 23, 23. So I write like that: 1, 2, 3, 4. Right. Notice that the 1 and the 0.3, I have to leave the 1 out by itself. And factor out the 0.23, we have 1 plus 0.01, 0.000. One. We do similar thing, and that will be so 0.23, and that is 1 over 100 to the k, and the rest will be similar. Right. I want to pay more attention to the next part because I think we did quite a few examples in the geometric series already. So for geometric series, just make sure that we have a to the r to the power the power cannot be at the bottom. If the power at the bottom, have to put one on the top and bring that inside as a power. And the series should start from 0 to n. If not, have to make that change. Bottom line, there's a formula for it, so it's not too bad. So that is the geometric series. The next part of it, we will have geometric series. I'm sorry, telescoping series. Yeah, I want to spend a little more time on this than the geometric series. Now, nice thing about this is telescoping series. Telescoping series is a kind of a series that the term itself will cancel with the next term and the next term. We'll see. Now, let's put 1 in here for K, and then put 2 in, 3 in, and 4 in, and then just keep doing that. Now, I put 1 in here first. That is where I put 1 in for K. Next, I'm going to put 2 in for K. That's exactly what the series does, right? And we'll just keep doing this. And you may ask, where do we stop? Of course we don't. We go to infinity, right? But let's say if we stop at n, so instead of go to infinity, we're going to stop at n, meaning we're going to put n in for K. In fact, we cannot even do that. If we stop at n, there will be a term before that, right? Which is 3 of n minus 1. So we go from n minus 1 and then n. Sorry, that was terrible. Let me write all of this again. So if we stop at n, that's what we have. Now let's remove the parentheses and simplify things. 1 over 3 minus 1 over 3 cubed plus 1 over 3 square minus 1 over 3 to the 4th 3 cubed minus 1 over 3 fifths. And then next we have 1 over 3 to the n minus 1 minus 1 over 3 minus 1 plus 2, so n plus 1. Right. So that's what we have. This. Now, the telescoping series is the kind of series when some terms will cancel itself. And we'll see that this minus cancel with that. Right? That term don't cancel though. This term, I think we need one more though. Pretty much if this continue, all the minus term will cancel out. So what's left? By the way, this one will not cancel with anything. This will cancel. This will cancel. We're left with 1, 2, 3, and 4. But then to say, why do we know those two terms with the minus will remain? And the answer for that is, it doesn't matter. Because when it goes to infinity, in this telescoping series, the only matter is the first few terms. Because at n goes to infinity, this goes to 0. Because we have a finite divided by infinity. So usually when we write the telescoping series there's minus something, don't worry about that. Those minus term at the end will cancel out because we go to infinity. What only matters are the first few terms that does not get cancelled. Those terms remain, and that's what we have. Those two terms remain. The minus should not be a problem when n goes to infinity. Right, so that is the kind of a telescoping series. I'm doing number 3 first and then get back to 2. Right, how we doing so far? The geometric series kind of simple. And this telescoping series, just write out the first few terms and then all the minus will take care by itself. They will cancel out. The only thing left is the first few positive terms. Right, but we should have a plus and a minus. That is the characteristic of a telescoping series. We should have something like that, a plus and a minus, which we don't have here. But luckily we do have these properties. So we'll rewrite that. right? Now, the telescoping series, when we do that, just put in a bunch of values for k, going 1 from 1 to infinity in this case. So we put 1 in for k, and then put 2 in for k, and then 3 in for k, right. Remove the parentheses. What do we have? ln of 2 minus ln of 1 plus ln of 3 minus ln of 2 plus ln of 4 minus ln of 3 5 minus ln of 4. So what terms remain? Do we cancel? When we cancel, the only first few terms will remain, right? So ln of 2 minus ln of 2, ln of 3, ln of 3, ln of 4, ln of 4, and then the 5 will cancel the 5. So when we cancel everything, oh, by the way, when I set the negative, doesn't matter. I mean, when they have the to the n power, it doesn't matter. So when we cancel everything out, the only thing left is what? So we're only left with this. If this one go indefinitely, and ln of 1 is 0, so we have 0. So let's see if we can kind of get the summation here. Right, math, option 0, has x be from 0 to 1000. We always can change the index, and then we have ln of fraction x plus 1 divided by x. Alright, let's see what we have. Sorry, cannot have 0. I guess that's why they start with 1. Right. Just let it run. Oh, if we keep ln of 5, the next one is going to be ln of 6 minus ln of sorry, this is not 0. Sorry, we should not do that. So that's why this is a good idea when we stop at n. So we should write. So ln of 5, I'll just keep ln of 5 minus ln of 6 minus ln of 5, and we keep doing that. we have ln of n plus 1 minus ln of n. And we'll keep going. Sorry, you're right. There will be a term remain at the end. So what term remaining here? So the 5 in it will cancel out with this. And then the 6 will cancel. So pretty much everything cancel out and we're left with this and this. Sorry, this cannot be 0 because all of them are positive. We should have something. And then so pretty much that sum is equal to this. And then when we let n goes to infinity, that one goes to infinity. So this series diverges. Yeah. So pretty much it will cancel out, and it will cancel out this term as well. As you see, then it will be confusing. Let's go back to the first one. What do we see? On the big scheme of things, the second term we got cancelled out. On the second term we cancel out. Right? Now, that's why we have to write this down. Then we see what cancel and what not. And so the minus, that cancel with this down the road, that cancel with that down the road. So we know that everything cancel out except for those two. Right. So in here we see that the ln, the first term is cancelled with the second term of the next, and we just keep doing that. Think about this way, not worry about the numbers at all. Let's just try to visualize this one as follows. If we have a bunch of dominoes, of course in the dominoes, the consecutive connecting so if there's connecting like this, there must be something left from the beginning and something at the end. That's exactly what we connect the dominoes like this. Since in these dominoes the second term cancel out, that one have to cancel out as well. Right. And also the hang off. So if you think about the dominoes like this, it's easy, right? It should be a first term and then the last term. So that's kind of like what a telescoping series does. Now the difference between these two examples is that one of them we start with k and then k minus 1, and the other one is k plus 1 and k, so kind of backward. But we should write out a bunch of terms and see what are connecting and what's left that does not get cancelled. So you're right, if we stop at 5, that will be left, we're left with ln of 5. If we stop at n plus 1, that's where we stop. So thanks for that question. Otherwise, that could be a mistake here. Right, back to 2. By the way, if we write like this, it's not going to help, because if like this, if we put 1 in, we have 1 times 1 times 2, and 1 over 2 times 3, 1 over 3 times 6. There's nothing cancel out. Remember, telescoping series have to be a difference of 2 terms, and it will work out just like the dominoes. Something will cancel with the next, and then something will remain. Right, so this is the simple domino. Sometimes the domino works out, doesn't work like that. Sometimes the domino cling differently. They cling this to this one as well, and then it link this term to that. And that's what happened in our first example here. And then we know that this term and if we just keep doing that, sorry, confusing myself here. Domino does not link like that. It's always the end that link to the first, right? So I have 1, then always the end link to the head of the other one, and this end will link to the head of the other one. So remember, the domino only drawn by the head and the tail, head and tail, like that. So it's not head and tail, so it's not that. So in this case, when everything link up, what's left? This one's left, this one's left, this one's left, and this one's left. And that's why in this terms there are 4 terms left, because what we're linking is the end of this guy with the head of the guy, not immediately after that, but the one after that. Let's skip one and then link a head to a tail, or a tail to a head, but not immediately, but the one after that. So try to write a few terms, and then when we do this kind of domino linking, and then we'll see. Right, now what is the 6? You mean ln of 6 here? Oh, we just keep increasing the n. Right. So I guess I will put this in as a domino kind of things. So think about all of this as a kind of a domino thing. Each one of them, there's ln of 2 and the ln of 1. The first one, the second, 4 and 3, 5 and 4, and of course the next one is 6 and 5, and then so on. Oh, sorry, that's 4. Right, now back to this. Remember, we only link the head to the tail of the other, this kind of backwards though, so we link like that. So it's always the head of this one with the tail of the other one. The head of this one with the tail of the other one. And the head of this one with the tail of the other one. So when everything link up, this term is left. That's one link, and this one's left. So left with Ln of 1. And then the last domino will be Ln of n plus 1 and Ln of n. We know that that part will be left. So we have Ln of 1 and Ln of n plus 1. That's what we have. This. Right. So the point here is it doesn't help if we write like this. Right. So we have to somehow split this. If we can write like that, and that will be helpful, right? By the way, this is just as a partial fraction. So we're going to do the partial fraction, try to split that into that. Right. Of course, here we multiply by the least common denominator of k and k plus 1. So we have 1 equal to a, k and k cancel out, k plus 1, b, k plus 1 cancel out, bk. Right, and of course we multiply them out by like terms. However, I'm going to do this a little bit different because this one is too simple. Usually when we only have simple linear factor like this is what we can do. Again, simple linear factors. If this one square or cube or something complicated, won't be able to do that. But with the first power, this is what we can do. Now, out of this, let's say what happened if we let k equal to 0. So what I try to do is I'm trying to make each one of this equal to 0. Now, if k equal to 0, we still have 1 equal to a 0 plus 1 and b times k, which is 0. So this of course is 1 equal to a. That's it, right? And then we will try to make this equal to 0. So let k equal to negative 1. K equal to negative 1. This is 0. We have 1 equal to negative b. So b is negative 1. So for a simple case, when we only have the simple linear factors, partial fraction, when we do like this without using the calculator or system of equation, that would be better. Right. Let's look at one example. Another example. I say if we want to do that and we're trying to do the partial fraction, multiply by the least common denominator, we have 12 equal to a x minus 3 and then b x plus 2. Notice the x plus 2 cancel out. We have x minus 3 and x plus 2. And from here, what we're going to choose is something to make the factor equal to 0. So I'm going to choose 3. So that cancel out. We have 12 equal to 5b. So b is 12 fifths. And then choose x equal to negative 2. So that will be 0. We have 12. By the way, we might have x on this side too. If there's x on this side, put 3 and negative 2 on this x. So if there's x here, so negative 2 minus 3 plus b, negative 2 plus 2. That cancel out. We have 12 equal to negative 5a. So a is negative 12 over 5. Right. Once again, if this is the linear factor, then it's easy. The problem is when we have like square or like this, it will start getting more complicated. In that case, I recommend just using the way we did before. Just use a calculator, system of equation. But if it just have no power on the power or on the factor, then that should be easy. Right? So bottom line is we write this as one over k plus 1 is the same as 1 for a minus 1 over k plus 1 for b. Or we should say this, which is of course. Right, now we'll go back to our problem. The series now becomes right. Now let's write this. Put 1 in for k. Right, put 1 in for k, put 2 in for k, three in for k, four in for k, and then we put what? N in for k. Right, let's go back to the dominoes again. Right, remember on the dominoes, if remember always the end connect with the head of something along the way. Now if that is the case, if we have the end of one thing, I mean the head of one thing and everything else cancel out, and the head cancel a tail, a head cancel a tail, a head cancel a tail, doesn't matter. At the end we should have a tail left, right? Next, on this one, we're not linking like we normally do with the one next to it. We're linking with the one that skips one unit. Bottom line is, when we do this, since we have two heads from the beginning, at the end we should have two tails, right? Because a head and a tail cancel out, a head and a tail cancel out. If we start with two heads, at the end there have to be two tails. That makes sense, right? If a head cancel with the tail, if one head from the beginning, there should be one tail at the end. So it's always like that, because one head always cancel with one tail. It might not be the one next to it, but it be something along the way. Let's think about that way. Now, if we think this big as a domino, kind of try to connect them. Usually a one with the plus, the one with the minus. Just separate the plus and the minus. Right? Now, the first one, negative 1/2, cancel with 1/2. The 1/3, cancel with 1/3. I have a bunch of different colors. Negative 1/4, cancel with 1/4. Notice that when we do all of this, the 1 remaining, right? So when we cancel out, up to this point, what do you think, which one of these will cancel out? Okay, so remember, when a head cancel a tail, a head cancel a tail, a head cancel a tail, if we have the head first, if the head remaining from the first one, we have to have the tail remain on the last one. Right, I hope it makes sense with the telescoping. And then this one, when n go to infinity, one over n plus 1 will go to 0 as n go to infinity. Because of that, this one go to 1. Oh, 1. Because that one go to 0. Right. Right. Let's take 10-minute break here. 5-minute break. And then we continue at 10:08. Yeah, we'll do one more before we go to the next one. Right, before we go to the next one, next section, let's just do the dominoes one last time. So again, a head will cancel with a tail. Let's say this one will cancel with a tail of the one on that term, so which is 3 terms down the road. So always a head cancel with the tail 3 terms down the road. And then the head cancel down with the term 3 terms down the road. Then we can have a few more of this. It's going to be 3 times down the road. I haven't used red. And then the head will cancel with 3 terms down the road. So what's left? So we know that starting from this term they got cancelled out, so we left with 1 end, 1 tail, 2 tail, and 3 tails. If we left with 3 tails, we should left with 3 heads, and so it will be 1, 2, I mark it wrong, should be that term. 3 head. So those are the term remain. Of course we know that in that term we match with that term as well. So if we if from the beginning we have 3 heads, we left with 3 tails on the last term. If we have 3 tails on the first term, we left with 3 heads on the last term, and so it's like that because the head will always cancel with the tail. Right, and I was wrong, sorry about that when I said the last term doesn't matter. The last term doesn't matter if that goes to 0. In this example, the last term go to infinity, so that definitely matters. Right. So that is that. Right. Section 10.4. So to recap, on the previous section 10.3, we learned about the series, and then the series is the sum of the sequence. So we have 2 types of series, geometric series and telescoping series. And we know when it is convergent and when it is divergent. Now, the divergence and integral test. One. Divergent test. Actually, the last example will be extremely helpful though. Talk about the telescoping series. Remember, on this series, if the last term go to 0, then it only matters the first term, right? Next one, the last term here does not go to 0. If the last term does not go to 0, then it have to be diverged. Next example, the last term go to 0, so the series converge in this case, right? But it's not. It's simple. So the theorem in divergent test is this: if the series converges, meaning that there is a sum, then limit equal to 0, then the sequence go to 0, the n term go to 0. Equivalently, if the limit does not go to 0, k go to infinity, ak not equal to 0, then the series diverges. Bottom line is, this test is called the divergent test for a reason. It only can test divergence. It cannot tell if the series converge. Now this note is extremely important, so definitely we need this. Divergent test only tests divergence. Of course, the particular, if we have k go to infinity of ak, if the last term go to 0, the test is inconclusive. So, only test for convergence. So there's only two cases. First, when the limit not equal to 0, that is divergence. If it equal to 0, infinity. If ak go to 0, then it is inconclusive. Right, so that is important. Kind of straightforward though. That is, if we can find the limit of the n terms. Sorry, I wrote the E like that. I just don't want to use the y out too many times. Let's look at the first example. By the way, I'm sorry I reset the Wi-Fi, but it doesn't help. It still have some lacking along the way. Right. So, by the way, when we go to section 10.8, we in this chapter we have like 10 different tests of convergence and divergence. This usually the first one I will use. The first one we test is see. If the n a term in the sequence, so let's take the limit of that. As k go to infinity. Right. You remember how do we do this? So this one kind of like polynomials, right? So let me try this again. As n go or k or whatever the variable, only the highest power term matters. So that's why we check the highest power term on the top and the bottom. Oh, when I'm talking about the test, I'm not talking about the actual test that you take. I'm talking about the test of convergence or divergence. So when we will see the problem, like we have a series. Most of the problem in this chapter is about this. I give you a series, and you will tell if it is divergence or convergence. And this is the first test that we use, usually. I just want to see what happened at the end terms. If the end terms does not go to 0, then it is inconclusive. By the way, the book that when I studied like 15 years ago, instead of divergent test, they call the end term test. Because we test for the end term when n go to infinities. But that does not it's not as clear as what we have here when we said about the convergence and divergence. So that's why I guess they changed to divergent test instead. But now we have one. By the way, if this is not equal to 0, then this is divergent. Two. Wow. just calculating how much how much time we will miss, and that's 63 about 6,000 frames, so that's about 3 minutes. By the way, if something I missed, please just type on the chat. I will explain again. I'm not sure what happened on the replay though. We still lag on the replay. I don't know. Anyway, so for this, so again, we'll take the limit of that term and see what happened. So what is the limit of that? So when k go to infinity, by the way, there's no thing on the top that we choose to take the highest power, because that's only one. So just going to put infinity in and see what happened. In this case, we have a finite divided by infinity. That is 0. So we have limit at k go to infinity of 1 over square root of k go to 0. What happened if the n terms on this case, the k terms go to infinity, equal to 0? The test will be inconclusive. So pretty much either we have divergence or inconclusive. This test cannot prove convergent. Three. K equal to 1. Now, of course, we will take the limit of that term and see what happened. Right. So what do we do here? Now let me ask you this. K go to infinity, right? So we have 1 plus infinity here. So obviously the 1 here is extremely small compared to 3 to the k. In fact, if we refer back to the note card that we have earlier, the constant is the lowest of order in the lowest order. The b to the k is the higher order. In fact, it's even higher than the power. So all of this, only the 3k matters. The reason we don't have 1 because 1 is significantly less than 3 to the k. As k go to infinity, that go to infinity, 1 stay at 1. So what we have is a geometric sequence, not geometric series, geometric sequence, just one term. And what's that? Right. Not today, but the last thing we learned on Monday was geometric sequence. If the ratio between -1 and 1, it is equal to 0. If it is bigger than 1, it does not exist. So in this case, if we don't even need to see that, we know that. By the way, 3/2 is 1/2, right? Now if we have 1/2 to the infinity power, that's where we put infinity into it. Of course, that equal to infinity. Oh, shoot, it keeps lagging. Let me reset the Wi-Fi again. I may have to use the wide connection because right now I'm connecting like 2 webcams, a microphone, and a lot of them like use a bunch of USB, like 5 or 6 USB right now. So that's why it might be a problem. So I might have to try the wide connection next time. So there should not be a problem, hopefully. Right, now let's try this problem instead. Like I said, it starts from 1 or 0, doesn't matter. What matters is it goes to infinity. Right, I'm trying to put a bunch of terms in here and see what happened. Sine x, a sine of k. It's spelled sin, but that's sine of k. K factorial. Right. I said I'll try to throw in a bunch of terms and see what happened. Right. Of course, it's not going to be this bad on the test, but so that's why we do this in class. Sync. Right. On the order of things. Right. Let me write this out. We have. So out of this, which one is the one with the highest order? Not just the highest power. By the way, k squared, square of k, and 2. We know that this one is the higher power than those two, right? So these three are easy. That to the power 1/2 is obvious. It's obvious that k squared is bigger than k to the 1/2, and bigger than 2, a constant. So out of those, so k squared and 3 to the k, which one is higher? So we look at this. The exponent is bigger than the power. So this is what we need. We know that already. But also 3 to the k is bigger than 2k squared when n go to infinity. Keep doing that. When k go to infinity, exponent is bigger than the power. So all of this will take the one with the highest power. It's going to be this guy. Remember, if the base is constant, will be bigger than when the base, if the base is constant, it's going to be bigger than when the constant on the power. So constant at the base is going to be bigger than the constant on the power. Because one of them is exponential function. For example, 2 to the x, and then the other one is parabola. Parabola kind of, it does not go to infinity as fast as exponent. So exponential function go faster than power function. So in that case, 3 to the k has higher than all of them. And out of those two, the sin k is even less than 1, which is even less than the constant. So that's why sin k doesn't matter. 5 to the k exponential function is less than polynomial. So in this case, the polynomial is the one with the higher power. So we check the one with the higher power. Ignore everything else. So that's why I said this is very important. So constant, ln, power, exponent, factorial, and n to the n. This is called, I think, super exponent. What is super power? I have to look it up, but that is the biggest one. This one with the highest order. So now compare those two. K factorial is bigger than the exponent. So this one is bigger than that. So when we divide them, it's going to be infinity. Right. Since k factorial grow faster than 3 to the k, when we divide them, the whole thing will go to infinity. Right? Because if it goes too fast on the top, the bottom are relatively small. So the bigger number on the top divided by the very small at the bottom, that will go to infinity. I think we wrote that somewhere before. If the faster at the bottom, let me just say this. If it is faster on top, it will go to infinity. If the faster term is at the bottom, it will go to 0. In this case, we have the faster term on the top, so that will be infinity. Alright, so that's why this is extremely important. Constant, ln, power, exponent, factorial, and then n to the n. And in the power, we can break down into a bunch of little powers. And then also it's in the n, in the b to the n, of course 2 to the n is significantly less than 3 to the n. We also have that within that rank. Right, so like I said, give this harmonic series. This should be a theorem. Right. The harmonic series, that one. If we put 1 in for k, 1 over 1, 1 over 2, 1 over 3, that is called the harmonic series. And the theorem says this series diverges. Even the terms get smaller, 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 eventually equal to 0. Even though when k go to infinity, that go to 0. So why is that? Right. So the beginning of the divergence test, we say that if the n terms equal to 0, if the last term when k go to infinity equal to 0, it is inconclusive. In this case, this one diverges. So the problem here is, even though it go to 0, but it does not go to 0 fast enough. If it does not go to 0 fast enough, it will be divergent. If it go to 0 extremely fast, it will be convergent. So bottom line is, we get back to this though. Bottom line is, the divergent test only tests for divergence. We need another test that can at least tell if it is convergent or not. Integral test. Right. Suppose f is continuous. Positive and decreasing. For x greater than or equal to 1, ak equal to f of k. Then the infinite series right, if we have and there's a note, even it is convergent, the sum is not even if there is convergence, the sum is not the integral. So bottom line is this test, man, is give I'm sorry, what? I'm sorry, what? Yeah, I don't know what you're talking about. Oh no, is that about this one? Oh, actually it is not. It says that it will tell the series will be convergent or divergence. Like I said, if you look at the first few examples, then we get the idea. But for now, yes, remember there are 4 things that we need to check. Right, so again, it's very important that even on the test they will ask you a few bunch of different things, but make sure that we need this thing. It's continuous, positive, decreasing, and then whatever the function equal to. So first, what we do is we're going to let the function equal to this. So instead of k, let's turn that to x and make that a function. That easy. Next part is we do the checklist. Swear. First one. Is this one positive? Sorry, continuous. And obviously this one continuous because k squared plus 1 is always positive. We don't divide by 0, it's always defined. So yes, is that positive? Also yes, because k is positive. Next, decreasing. This require a little bit of work. To check for decreasing, we will take derivative, which is the quotient rule here. V square u prime v minus u v prime. That's the quotient rule. And when we do this, negative k square plus 1 square. The square is always positive, so this one is negative. And if it is negative, derivative is negative, therefore this is decreasing. By the way, on the test, if they ask you to use the integral test, all of this have to check, otherwise we cannot use integral test. By the way, also there's a box. Let's say I think is f of k equal to h of k for k equal to 1, 2, and we only have to check that box as well. So there will be a question like this on the test. There should be 4 boxes that to check: continuous, positive, decreasing, and that. And when all of that satisfied, we will use the integral test. So the integral test will take the integral of the function from 1 to infinity. And we cannot, section 8.9, we cannot take integral if one of them is infinity. So we let b goes to infinity and go to from 1 to b instead. And we have the function, this should be x, sorry. This should be x. But I guess k is fine too. But when in the integral, we should use x. Yeah, all of them are x's. Right. So, because of infinity, we have to change the limits to b. So, all the done, we check all of these things. All we do here is just, instead of the sum, we do the integral. And that improper integral, we have to change the limit. So that's what we are at the moment. Right. And then integrate this. This is just a substitution. So let u equal to x squared plus 1. And then take derivative. Move the dx over and so for dx. And then also the limits. X equal to 1, u is 1 squared plus 1 is 2. X equal to b, u is b squared plus 1, just b squared plus 1. When we substitute all of this back into the integral, we will have x over u du, dx is du over 2x, and of course we change the limit already. So this is b squared plus 1 and 2. Right, so just integrate. X cancel x. Take the 2 outside. And the integral of 1 over u is ln absolute value of u going from 2 to b squared plus 1. And we have limit b go to infinity. Now we're going to put b squared plus 1 and subtract, put the 2 into it. And finally b goes to infinity. If we substitute that in there, ln of infinity of course is infinity, so that term goes to infinity. So it is infinity. By the way, back in section 8.9, when we say if the integral equal to infinity, that is divergent. Since the integral divergent, the series is divergent as well. By the way, if whatever the integral come up with a constant is convergent. If the integral is convergent, the series is convergent. So essentially that's what the theorem is about. So in fact, actually we should do something very easier than that for first example. Try this example instead. Remember, this is the harmonic series. And we did say that it is divergence. Right. So, first we let the function be exactly like the term in the sequence. Instead of k or n, or change that to x. Right. And we're going to check these four things, which is continuous, positive, decreasing, and the last box, f of k equal to a of k. By the way, the last one we check for sure because that's certainly the case. That's what we make it equal to. Right, continuous, yes, because x greater than 1. Oh, by the way, it's go from 1 on. So certainly if it is bigger than 1, we don't divide by 0. if it's continuous. Is that positive? Obviously yes, because if x is positive, 1 over x is positive. Is that decreasing? And that also yes. We don't need to take derivative because if we divide something that is decreasing, the x is increasing. If the bottom I just write here bigger denominator, smaller quotient. That's what we have. It is decreasing. So the bottom getting bigger and bigger, the whole thing gets smaller and smaller. Therefore, it is decreasing. We don't even need to take derivative. Bottom line is all of this check. Now we will take the integral 1 over x dx from 1 to infinity. Right. Improper integral integral 1 over x is ln of x. Put b in it and put 1 in it. B go to infinity. Ln of infinity is infinity. So we have infinity minus ln of 1, which is 0. So this is infinity, which is divergent. If it is divergent, the series is divergent. If it is convergent, the series will be convergent. Well, apparently we only have like about 30 more minutes in this section and then we're ready for the test. But like I said, we still need 30 minutes. So I will not post the test today, even though I have the test ready already, but we are not finished this section yet. So I'll post the test on Friday. So after Friday, certainly we can take the test. We should have everything. All right. Yes, I'm going to post the note on Thursday because we definitely need the note by Friday. So once again, I'm sorry about the problem. I got that some problem last night, like very late last night. I didn't go ahead and reset the modem, which I should. So do you have any question before I end the stream? yeah, the technology thing that was unexpected, and I'm not sure if I can fix that in the middle of the video and still have the same video, because obviously I record everything, but if I combine the video that I recorded, I post it up, and then on YouTube it will take one or at least 2 to 3 hours before it's ready. So I don't think that's good. Yeah. And about the fast paced thing, and that, don't worry, I mean, we have the test review as well, right? So it just refer to, we have quite a few questions like this on the review, and certainly will be on the test as well. So we should go over this again on the review, right? Again, sorry about the technology things, because I said I didn't expect it, and we cannot fix it midway though, right? So right, other than that, have a nice day. See you on Friday. I will post the test after we done on Friday.